Welcome back. We've been discussing quantization noise, and we finished last time with the remarkable result that the quantization noise level is independent of the signal as long as the basic requirements are met for our assumptions. And those requirements were that the signal did not saturate and that the signal crossed multiple quantization levels between samples. And the reason for this was we could then model the signal as white noise and do the statistical analysis on that. So as long as we have a signal that isn't saturating and that is sufficiently large or fast moving, then the noise power is completely independent of anything else about the signal. Well, now that we have this, we can talk about the signal to noise ratio, and that's what really matters in a lot of situations. This SNR, as it's abbreviated, is what we are concerned with when we look at audio quality, when we decide how many bits we want to use, and so on and so forth. SNR is signal power over noise power, and this is usually expressed in decibels. In decibels, the SNR is equal to 10 times the log 10 of the SNR, because SNR is in terms of power. So we use the 10 out front instead of the 20 that you'd use if you're talking about amplitude. Okay, so now let's go ahead and look at what happens if we want to explore the signal noise ratio with a typical signal, and we'll start with a sine wave. At some point in our careers, we've run across something like this, and we know that the power of such a signal is going to be, let's see, is P. I know we use P for a lot, but this time it means power. A squared over 2. So now we can find the SNR. SNR is going to be A squared over 2 divided by delta squared over 12, which means we have 6 A squared over delta squared. So in computers, in fixed point processing, and when we're not using floating point numbers, there's a notation called Q notation, or Q format. In Q format, you have, for example, if we have 16-bit data, we don't specify that with the Q. What we specify is the fractional bits. So in other words, the radix point is going to be just to the right of the sine bit. And this gives us -1 to 1 representation. So that's essentially what we've been talking about and what we've seen before. If we let A equal 1, in other words, we've maxed out our operation, it'll maybe touch on saturation occasionally when it tries to hit 1 straight up, but we're going to ignore that. We would have that the signal to noise ratio is now equal to 6 divided by 2 to the negative 30th, 98 dB. So 98 dB signal to noise ratio, is that good? Yeah, that's really good. Our range of hearing is approximately about 110 dB. So what that means is that if you had something uncomfortably loud, the noise would be down there near your threshold of hearing. So a signal-to-noise ratio of 98 dB is great. However, those are pretty ideal circumstances. This is one tone maxed out. And the problem comes if you're trying to listen to especially something like a classical CD, which I frequently enjoy, and it starts out at the beginning of the song with the violins sotto voce. You can barely hear them, and so you turn it up so you can hear those, and now you have quantization noise. You can hear the hiss behind the violins. Why? Well, it's because the actual amplitude of those violins is very, very small, and they had to do that because later they're going to be blasting the kettle drums and everything else, and so they had to turn the signal down enough that those kettle drums wouldn't saturate. So that's a problem. Another problem is that while sine waves don't perfectly max out the energy that you can get, they do a pretty good job. Compared, for example, back to the drums, a drum may have a big spike, and you can't let that spike saturate. And so that spike, which only occurs periodically, represents low overall energy, but high instantaneous power. So it's a complicated situation, but there's a very useful result that we can get. And that is, let's look at what happens as we change the number of quantization levels. We'll start with the basic setup that we had before. We have some range full scale. Delta is going to be range full scale divided by 2 to the b. So we're assuming, again, that we have a binary representation, which is a very good assumption. So, under these assumptions, and none other, let's just look at signal-to-noise ratio. Signal-to-noise ratio is going to be the power of the signal, whatever that is. We don't know. Let's just put it there. Divided by the power of the noise. And the power of the noise is going to be delta squared over 12. So this is going to be RFS squared divided by 12 times 2 to the 2b is equal to 12 times 2 to the 2b times the power of the signal divided by RFS squared. So there's our signal-to-noise ratio. Now, SNR in dB, give myself some room, will be equal to 10 log 10 of SNR which is going to be 10 log 10 of 12 times 2 to the 2b PS over RFS squared. And using the laws of logarithms, we'll divide this up a little bit, and we get 10 log 10 times 2 to the 2b plus 10 log 10 of PS over RFS squared plus 10 log 10 of what's left, which would be our 12, and that's going to be about 10.8. Okay. So this is a function of the signal power. This obviously is a constant. And this is interesting because this can be written as a function of b, because b will come out of the log and give us 6.02 times b. So our signal-to-noise ratio is going to have some constant that just shows up because of the way the math works out. And obviously, since we're looking at signal power versus the ratio of noise power, it's going to be a function of the signal power. But the most important part is it's also a function of the quantization level. And as you increase the quantization level by 1 bit, you increase the signal-to-noise ratio by 6 dB. Now, we don't exactly know what these other quantities are. But one thing that we do know is that this middle term is negative. Or at least non-positive. It's negative or 0. Why is that? Well, the power of the signal could never be greater than range full scale squared. And in fact, if the signal were just maxed out at the highest value, let's use numbers here to help out. For example, if RFS is equal to 2 plus or minus 1, then power of the signal is going to be equal to 1 squared. So the maximum PS over RFS could be, under these simple assumptions, is 1/4. So 10 log 10 of 1/4 is going to be approximately 6. So this value is going to be less than or equal to about -6. What does that mean? It means it approximately cancels that constant term over on the right. We're never going to hit full power. It would be a very uninteresting signal. And so it'll almost certainly be less than -6. And under those circumstances, -12 would be a reasonable place to start, which is going to cancel out that constant, meaning that this whole thing, SNR in dB, is going to be approximately equal to B, or 6.02 times B, under those assumptions. Okay, so is this right? Well, if we have 16 bits, 6 times 16 is 96. 96 is what we actually, almost what we got for our sine wave, which is 98. If you look at the specs, the signal-to-noise ratio specs of sound cards, you get numbers usually between 80 and 98 dB. So in the ballpark range.